video, I want to take a look at an example problem of using general planar motion to solve a system. So in this problem, we've got a piston, which is connected to a connecting rod, which itself is connected to a crankshaft. And I've kind of got all of those pictorially represented in simplified form. If we're given, or we know the rotational speed of the crankshaft at 2000 RPM, and we want to find the velocity of the piston as it's moving forward, how do we go ahead and do that? Now, what we're looking for here is the instantaneous velocity, because the velocity of the piston changes over time. So we're going to define that the crank arm is at a position of 40 degrees here, with a line that passes through points A and C in order to kind of better define which exact point in time it is that we're looking at. So usually with this kind of problem, it's best to start at the end, or with the rigid bodies that we know something about. So in this problem, we know the most about this rigid body connecting points A and B. So if I pull out that rigid body by itself, I know that it's fixed at point A, and I know that it's rotating at 2000 RPM, and I know that it has a length of 3 inches. So the most obvious thing that I can solve for in this problem, knowing that we have basically a fixed axis rotation, is I can solve for the velocity of point B. Now this velocity is what we would consider an absolute velocity, meaning that it's referenced to ground, right? There's point A is not moving, so the velocity of B is with respect to A, and A is not moving, so it's a ground referenced velocity. So that makes it kind of nice to work with. So I can use my equation for rotational fixed axis rotation systems, which says that the linear velocity of any point on that rigid body is equal to the length, or the arm between the center of rotation and the point that I'm talking about, multiplied by the angular velocity. So for this problem, I have 3 inches as the length between A and B, and I'm going to multiply this by 2000 revolutions per minute, and I'm going to multiply that by 2 pi over 60, which is converting revolutions per minute into radians per second. As a result, multiplying that out, I get 628.3 inches per second as the velocity of point B. So we know pretty much everything about rigid body AB. Next, we would move down the line and start looking at rigid body BC. Now, in this case, it's a little bit more complicated, right? We have this rigid body connecting points B and C. Point C is sliding back and forth. It's constrained in the vertical direction on the screen, but free to move in the horizontal direction. Point B is seeing rotation, so there's kind of a complex motion going on here, right? But the principle of general planar motion still applies, in that we can break this system down, this general planar motion down, into translational and rotational components. And that's useful because we know something about point B and what it is doing. So if I break this down, I'm going to separate out the connecting rod BC, and I know that this point B has a velocity VB, like that. And because I'm forgetting about the rotation at this point and just focusing on the translation, I'm going to apply VB to point C as well. So this is our translation of B. Now, of course, we can see that this is showing point C moving kind of down and to the right, which we know can't happen, right? Because the piston is constrained only to move left and right. So we have to fix that by rotating point C up and fixing point B such that we have a fixed axis rotation. Now, the velocity of point C in this case is no longer with reference to a fixed frame of reference. So, as I stated up here, the velocity of B is being referenced to ground. The velocity of C is being referenced to point B, which itself is moving. So we're going to use something from relative motion and say that this is the velocity of C with respect to B. This is the rotation about point B. And now I've got a situation that I can look at. And the key equation that we're going to pull to analyze this is the relative velocity equation, which is going to say that we can calculate the velocity of point C, the absolute velocity of point C, as the velocity of point B plus the velocity of C with respect to B. And this is from relative velocity that we've discussed before. So now we can start looking at what it is that we know about this system. All right, so giving myself a little room here. We know that a vector equation like this can be represented graphically. So I'm going to go ahead and say we have the velocity of C, like that. And I've drawn this horizontal because we know that C, the piston, is constrained to move horizontal. So the velocity has to be in that direction. And that's key. We really want this graphical representation to contain all of that information and what we know about it. I also know the direction of VB, roughly shown as being down in this direction. And if I look up at my original drawing, I know that the velocity of B is perpendicular to the arm connecting A and B. And because this is a 40-degree angle here, if I form a right triangle, I know that this angle here with respect to the horizontal must be 50 degrees. So I can go ahead and represent that here by drawing VB, which we know the value of. It's 628.3 inches per second. And the angle I was talking about is this one, which is 50 degrees. Finally, I know that if I add VC/B to VB, I should end up at the same point. So I'm going to draw this line up here and label this VC/B. Now my drawing here isn't to scale. Of course, if I knew enough information and I was doing this carefully, I could draw it to scale and take measurements and solve for vectors that way. I'm just using it as a visual representation to kind of see what I'm doing. So one thing that would really help us would be some information about the orientation of velocity CB. So I want to know something about the orientation of this connecting member BC. So let's off to the side draw a little triangle which represents our physical system, A, B, and C. I know that this length between A and B is 3 inches, and this length between B and C is 8 inches. I was given that this angle is 40 degrees. And what I'd really like to know is this angle over here, let's call theta. So something that we can use to solve this and figure this angle out is the law of sines. So the law of sines would give me that the sine of 40 over 8 must be equal to the sine of theta over 3. So this angle corresponds to the side length of 3, and the 40-degree angle corresponds to the side length of 8. So using this and solving for theta, I get something like this. And that gives me an angle of 13.95 degrees. All right, so to kind of visualize where this actually goes now on our vector triangle, I'm going to bring this up here. And this angle I just solved for is this one right here. Has 13.95. Because VC is perpendicular, or VCB, excuse me, is perpendicular to BC, I can say that, well, measured off the vertical, this angle also has to be 13.95. So that I can represent over here on my vector triangle if I draw a vertical line and label this angle here. All right, so I'm getting pretty close. Let's see what else I need. So I'm going to actually employ the law of sines again to get an equation such that we can see what we actually want to solve for. Ultimately, we're trying to solve for VC, which means I need to know this angle here. And I need to know also this angle here if I want to be able to make use of my known velocity to solve for VC. So I can see from my triangle that I have a right triangle over here on the left. If this is 50 degrees, then I know that this must be 40 degrees, which we've actually already used. And therefore this overall angle must equal 40 plus 13.95 equals 53.95 degrees. Finally, I want to get the angle on this side, which corresponds to velocity of point B, and that angle I can see right away is going to be 90 minus 13.95, which means that it's going to be equal to 76.05 degrees. All right, so using these two angles, I can again use the law of sines and say that 628.3 over sine of the corresponding angle, 76, must be equal to the velocity of c, the magnitude of that velocity anyways, divided by the sine of the corresponding angle, which is down here, 53.95. Using that, I can solve for the magnitude of VC and say that it's equal to this expression. Great. So because point C is located on my piston, I've solved for my piston velocity, and I know that at this instant in time with the geometry given, it's moving to the right at 523.4 inches per second. Now, of course, if I wanted to, I could solve for VC/B as well. I could solve for that velocity. That would allow me to come back up here and solve for the rotational velocity of member BC if I wanted to, and I can basically fully specify, fully carry out every calculation I would need for this system, given that information. All right, thank you.